This video looks at some worked through examples for Combined Science Physics Paper 1. This is focusing on the particles topic and specifically on higher tier questions. So let's start with question 1. So a student is determining density, so that's what this question is going to be about. A cube made of bronze, and they're using a balance to determine the mass. So the first part of the question is asking what kind of error is shown on the balance. So there's nothing on the balance, but it's already reading 4.2 grams. So this is a zero error, but you can also call it systematic because zero error is a type of systematic error, as in it's systematic every single time you use the balance, you're going to get the same error of 4.2 grams. So either of those. How can we get a correct value? There's two possible answers. You could just say zero the balance, so in effect get rid of the error, but you could also say subtract 4.2 grams from each result. Either of those is fine. In effect, the first one you do before the experiment, the second one you might do if you've already taken a whole lot of readings. Part C, the student is measuring the length of the bronze cube using either vernier calipers and then using a micrometer. So these are both pieces of equipment we use to measure small lengths. We then got the results in table 1, so just make sure you read table 1 before you have a go at the question. It's showing us that the vernier calipers measure 20.1 millimeters, the micrometer measures 20.14 millimeters, and then we're asked to complete the sentence. So it's showing that they have a different, and the word we're looking for there is resolution. So remember, resolution means the smallest possible change that I can measure using a particular instrument. So if I look at the calipers, I can measure to the nearest 0.1 millimeters, but if I look at the micrometer, I can measure to the nearest 0.01 millimeters. So I can measure a smaller difference in length. That's why they've got a different resolution. Part D, student adds water to a measuring cylinder because they're going to use that to find the density of the bronze coin. It then says figure 2 shows the student reading the volume of the water in the measuring cylinder, so we can see that figure bottom right, and we're asked for 2 changes they can make to increase the accuracy of the volume. So don't forget, accuracy means a measurement which is close to the true value. So hopefully this is a fairly obvious one, but the 2 things we can change are obviously put the measuring cylinder on a flat surface. As we can see there that the surface of the water is tilted. And then secondly, something about bringing our eye down to the water level. Okay, so we need our eye level with the surface of the water. So there's our 2 points there. Okay, looking at part E, we're describing how the student can use the displacement method to find an accurate value for the volume of a single coin. Now, before we start planning the answer, let's unpick the question. So we're finding volume here. It doesn't say density. It's very tempting to write out the whole density method because we're familiar with that. It's about volume. Secondly, we're being directed to the displacement method. Now, we can use the Eureka Can, but as we can see from the previous slide, we're going to use the method where we measure the volume of water, add the object, look at the change in volume, and we know that that change is equal to the volume of the object. So that's the method we're going to describe. And then it says we want an accurate value for a single coin. We're told in the previous part of the question that the coins are very small. So what it's really saying is if I just put one coin in, I might not be able to measure the change in volume very accurately. And remember, we want an accurate value. So in order to get my 3 marks, again, I'm going to put 3 bullet points to remind myself to write 3 separate parts to the answer. So the first one I'm going to do then is say I'll use, and I'm going to pick an arbitrary number, say 10 coins. I'm going to measure the volume of water, then add the coins and measure again. Calculate the difference and divide by 10. Putting say in brackets there because you don't have to use the number 10. I would say anything from 5 above is okay, but 10's a nice easy number to divide by. So for 3 marks there, one of those is saying I'm going to do 10 coins and divide by 10. That's going to get our mark for accuracy. We're then showing that we know the displacement method, that is, we have to measure the volume before and after and find the difference. There's our 3 marks. Question 2. Figure 1 shows a diver, which 2 sentences describe the movement of air particles. Tick 2 boxes, and then I'll go on about this, but if it says 2 boxes, tick 2 boxes. So let's just go through, and then I always recommend read every single sentence before making your decision. So we know particles don't vibrate around fixed positions in a gas, but we know they do move in random directions. We know the motion is not predictable because it's random. We know that they do move with a range of speeds. So particles in a gas are rapid and random. They don't move in circular paths. We've got our 2 boxes. Part B. The temperature increases inside the canister. What happens to the movement of the air particles? So just the movement. So we've got a couple of things we could write here. We can say that the particles speed up. We could say they get faster. We could say that their kinetic energy increases. All of those would be fine. Then we're going to move on to C. Why would it be dangerous if the temperature increases by a large amount? Explain why. Again, let's just double check. I've got 2 marks, so I need 2 bullet points. So the first one then is going to relate back to part B. We said the particles are getting faster when they're hotter. That means they'll collide more often with the inside walls of the canister, which is going to increase the pressure. So for our first point, we need to say that as the temperature increases, then the pressure will increase. There's our first point. So now we need to explain why that's dangerous. Well, obviously, if the pressure gets too high, then the canister could explode. And there's our 2 marks. Next part of this question then, we've got a canister of air and it's tested to find out how the pressure changes as it's used by a diver. So obviously as the diver is using up the air in the canister, then there's less air in the canister and the pressure's dropping. So the way they did this was to allow air to escape from the canister and then to record the pressure every 5 minutes for 80 minutes, and the results are shown in figure 2. So over here in figure 2, we've got time in minutes. You can see they've taken a reading every 5 minutes and they've got the pressure in megapascals every 5 minutes. Part D asked me to estimate atmospheric pressure. Again, we're using figure 2. So if we think about something like a balloon, if I blow it up and then let the air out, the air will keep rushing out of the balloon because the air in the balloon is under a higher pressure. Once the air pressure inside the balloon and outside is the same, the air won't come out anymore. That's why when we pick up our balloon off the floor, there's a little bit of air left inside because the 2 pressures are now the same. So we're looking for the point at which the pressure inside the canister is equal to atmospheric pressure because the air won't come out anymore and the pressure will remain the same. So we're looking for where the graph goes flat. And if we read off, again, much easier for you to do this on the full size graph with a pencil and ruler, but it comes out at 0.1 megapascals. Part E tells us that divers can stay safely underwater until the pressure has reduced to 25% of its original value. So what this is telling me is I'm probably going to have to do a percentage calculation. It then says determine, so work out the maximum time the diver can safely stay underwater. And again, it directs us to use that graph. So you need to use that graph. So let's start off with original value. The original value of the pressure is going to be here. That's time equals 0. And if I read off of there, that will be 2.25 there. So the original value of the pressure is going to be 2.25 megapascals. So we're going to get a mark for correctly identifying that. So again, if you're not sure about these questions, look at the information, look at what the question's asking, and do anything you think you can, because you'll pick up marks for everything that's correct. We now need to work out 25% of this value. So I'm going to do 25% multiplied by 2.25, and that comes out at 0.56 megapascals. So far I've picked up 2 marks. Okay. If for any reason I don't read the first number correctly, but I correctly work out 25% of that, I still get that second mark. And if I get the original pressure correct, but muck up my 25% calculation, I still get the first mark, which is why it's worth trying every part of the question, because you'll pick up marks for everything that's right. We've now got to find the time. Obviously, we've got a graph there with time on it. So if I find 0.56 megapascals, which is approximately here, again, on the original graph with a pencil and ruler, you'll find it much easier to do. And if I read along, it should come out, according to the mark scheme, just about here on about 27 minutes. So the answer should be 27 minutes. Now you've got a bit of leeway. I think the mark scheme allows you between 26 and 28 minutes. And again, if you've calculated 0.56 incorrectly, but read the correct reading from the graph, you'd pick up that third mark. And then on the last part here, we're being asked what happens to the volume of the air when it's released from the canister. And again, just think about air leaving a balloon. It's going to spread out, which means that the volume is going to increase. Question 3. The particle model can be used to explain the properties of gases. Question A asks us to describe the direction of motion of particles in a gas. So just the direction. So all we need to say here is that it's random. You could also say they're moving in lots of different directions. That would also be fine. Part B asks us to explain why heating a gas increases the average speed of those gas particles. So it's an explanation. There's 3 marks, so I need to have 3 separate bullet points. I don't think this question is conceptually very difficult. I think the difficulty comes in trying to stretch the explanation out across 3 marks. So let's start with the heating bit. The first obvious point then is that heating the gas causes the temperature to rise. Again, an obvious point that we sometimes forget to make. So heating the gas increases the temperature. The second point is for saying, therefore, the kinetic energy of the particles increases. And then going back to the question, we need to end up talking about average speed. So the speed of particles increases. So not a particularly difficult question, just very difficult to tease that out into 3 separate sentences, I think. Part C, water can exist either as a liquid or a gas at 100 Celsius. So this is this idea that because it's the boiling point, liquid can either be water about to boil or water vapour that's just boiled. And what they're asking us to do is explain why the gaseous water has more energy. I don't think, again, that conceptually that's difficult. We sort of know that anything which is a gas is going to have more energy. We need to say why. And there's 2 points to make here. So again, I put down 2 bullet points. The first is that energy is needed to break bonds when the water boils. So energy is needed to change the state from liquid to gas. What this is saying is that we've had to add energy to the liquid to make it become a gas. So it must have more energy. And the energy is needed to break bonds. So energy is needed to change state from liquid to gas by breaking bonds. And again, I think the most difficult part of that question is teasing that out into 2 full marks worth of an answer. Part D. So we've got water vapour is a gas. It changes state when they cool, and the figure on the right there is showing condensation on a cold bathroom mirror. Then we've got some data. So the givens we've got are that the volume of water on the mirror is 2.5 times 10 to the minus 5 meters cubed. We're told that the density of water is 1,000 kilograms per meter cubed. We're told the specific latent heat of vaporization is 2.26 times 10 to the 6 joules per kilogram. And my unknown, I'm asked to calculate the energy released when the condensation forms. So let's just have a look at what we've got. We've got the volume, which we know. We've got the density, which we know. We've got the specific latent heat, which we know. And we're asked to find energy, which we don't know. That's our unknown. Now, if I go to the equation sheet, I won't find any equation with those things in it. So there's going to be 2 stages to this question, and that's what makes it a little bit sneaky. So what I'm going to start with is, I do know that there's only one equation which has got density in it, and that's that density is equal to mass divided by volume. I also know there's only one equation with specific latent heat in, and that's E equals m times L. So energy is mass times latent heat. I know at the moment the density and the volume, the energy I don't know, but I do know the latent heat. So it looks to me like I need to work out mass first and then put my result into here so I can work out energy. Again, if you're not sure how to tackle these questions, calculate anything that you can think of that seems to be sensible, because you will pick up marks. So although I'm going to show you the full answer, don't forget it's better to try part of the question and pick up some marks than just to decide it's too difficult. So let's start off then. So let's go for density is equal to mass divided by volume, and I'm going to put the numbers in. I'm just going to have a quick look. The units are all in meters cubed, kilograms and joules. There's nothing there to worry about. So having selected an equation, I can just substitute straight in. So I've got 1,000 is equal to mass divided by the volume, which we're given here is 2.5 times 10 to the minus 5. You can also see here why I like to write the letters next to the numbers. So now when I go to put the numbers into the equations, I can clearly see that that's V, and I need to put it into V in this equation. Now to get mass, I'm going to have to multiply both sides by 2.5 times 10 to the minus 5. At the moment, mass is divided by that number, so I need to multiply to get mass on its own. So I've got 1,000 multiplied by 2.5 times 10 to the minus 5 equals the mass, and that comes out at 0.025 kilograms. So I've now got another known. I now know that mass is 0.025 kilograms. So I now know mass and latent heat, and I'm trying to find energy, which means that my second equation is going to do the job for me. So let's put my second equation, energy equals mass times specific latent heat. I don't know energy, I've got to calculate it. I know the mass is 0.025 and I know the latent heat is 2.26 times 10 to the 6. Put that into my calculator, I end up with 56,500 joules. So that's the answer that I mustn't forget to put down here, 56,500 joules. So again, even if you find that quite difficult, remember you're going to get marks for calculating the mass, so substituting in here correctly, getting the correct value for mass, substituting in here correctly, and getting the right value down here, and then also for substituting in the correct value of mass. So every step you get that's correct, you will pick up marks for. So question 4 here has a lot of information in it, so we're just going to break it down. We're told the student is using the apparatus in figure 1 on the right there to obtain data to calculate specific heat capacity. Now that should look familiar to you, along with the information below, which is the method for finding the specific heat capacity of an object. So we're going to take the initial temperature, switch on the power supply, measure the energy transferred using a joule meter, measure the temperature every minute so we can get the increase, and then the graph on the right is showing the student's results. Now just one little thing I noticed on this graph hasn't come up properly is that this should say here energy in joules. So I'm just going to add that at the bottom here. Going back to our question then, A says that energy is transferred through the copper block. It's the copper block that's important. What's the name of the process by which the energy is transferred? So that is going to be conduction. Remember, conduction is how heat energy is transferred through solids. Part B, we're going to use figure 2. So we're going to need to use that graph to find out how much energy is needed to increase the temperature by 35 Celsius. So again, if we go across here, we've got an energy along the x-axis and we've got the temperature increase along the y-axis. We're told that the temperature increase is 35, so we're working at this point here, and I need to read off the energy from the graph. Now again, much easier to do on the original graph with a pencil and ruler than it is with my slightly wobbly electronic pen, but when we read down, it should come out about here, it should come out about 35,000 joules. And again, on your original sheet, you should be able to see that a little bit more clearly. Part C. We're told here that the copper block has a mass of 2 kilograms, and then we're asked to go back and use our answer to part B. So before I read the rest of the question, I'm just going to put on here, we calculated that when we had a change in temperature of 35 degrees Celsius, we looked it up on the graph and we found that the change in energy was 35,000 joules. So that adds to our list of givens. We know the mass is 2 kilograms, the change in temperature is 35, and the change in energy is 35,000. We're now asked to calculate the specific heat capacity. We're also asked to give the unit. So we've identified our knowns and we've identified what we are, our unknowns, what we're looking for. We now need to identify the correct equation. There's only one with specific heat capacity in, which also has mass, change in temperature, and change in energy and specific heat capacity, and that is change in energy equals mass times specific heat capacity times the change in temperature. So now we need to put the numbers in. Again, put the numbers under the right letters so we don't make mistakes with our maths later on. Change in energy is 35,000. Again, by labelling up here that 35,000 is change in energy, it helps me remember to put the number in the right place. Mass is 2. I don't know the specific heat capacity, that's what I'm trying to find, and I know the change in temperature is 35. Again, I prefer to simplify the equation before I try to solve. 2 times 35 is 70. It now looks nice and simple. To get C on its own, I'm going to have to divide both sides by 70. So that's 35,000 divided by 70 will equal specific heat capacity, which is 500. So I've got 500 is my answer, but don't forget I've got to give the unit, which is going to be joules per kilogram degrees Celsius. And again, there's 3 marks here. I'm going to have 1 for substituting the numbers incorrectly. I'm going to get 1 for the correct answer and 1 for the correct unit. So again, making sure you've got that unit down there, even if you get the wrong answer, you do the maths wrong, you still get the unit mark. Part D then. This time we're asked, the experiment does not give the correct value, suggest a reason why. So what we're really saying here is what is wrong with our method. And it's a nice simple one there. Obviously heat energy, when we're heating up that copper block, some of that heat energy is going to escape to the surroundings. So the change in energy we're measuring isn't just going to the block, it's also heating up the air around it. So we can just say here, heat escapes or dissipates. This is always a nice word. So heat energy dissipates to the surroundings. Question 5. The figure on the right shows a cool box, and we're told that it keeps food colder than the surroundings, and it consists of plastic walls with a layer of polyurethane foam between them. It says that the polyurethane foam has a low U value. Why does it need to have that? So really what this question is asking is, what do we mean by U value? So a U value, remember, is it's a number that tells us how well something conducts. So a high U value is a good conductor, whereas a low U value is a poor conductor. And of course, things that don't conduct heat energy very well are called insulators. So low U value means a good insulator. Or you could say means it's a poor conductor. Part B, the foam contains air bubbles, and then it says explain how the air bubbles reduce energy transfer. And it says you should refer to the processes of energy transfer in your answer. So we've already done this a little bit in previous questions. Remember, processes of energy transfer, we're referring here to conduction, convection and radiation. Now we've got 3 marks, so again I'm going to put 3 bullet points in to try and make sure that my answer doesn't miss anything. So the first point I'm going to make is that air is a good insulator. So you do get a mark for just stating that. And then to make that answer extend to 3 marks, we can explain that it reduces conduction, because obviously conduction can't happen in a gas. And then for our 3rd mark, we can also mention that because it's trapped air, so the air can't move around to the surroundings, because it's trapped air, it also reduces convection. And there's our 3 marks. Let's see. An ice pack can be placed inside the cool box, and the ice pack contains a material with a very high specific heat capacity, and it's frozen and cooled down to -18 Celsius before being put in the cool box. The ice pack keeps the contents cooler than the surroundings for a long time. Describe how. Now again, conceptually, I don't think this is a difficult question. We all know that putting an ice pack in a cool box keeps the stuff cooler for longer. It's the explaining why which is harder. And that's because we've got to state the obvious, and quite often in an exam we forget to do that. Now there's 3 marks, I'm going to put 3 bullet points. So the first very obvious point to make is the ice pack is colder than the rest of the contents. So you get a mark for saying that, even though it might seem obvious. You can have a mark for saying that that reduces the overall temperature of the box. And therefore, more energy is needed to increase the temperature. And again, I think the difficulty of that is not that we don't know that, but how we spread that out into 3 marks. So hopefully that's given you a useful demonstration. I think with particle topics in paper 1, there are a lot more wordy answers. So I've tried to reflect that in the questions that I've chosen in this video. So hopefully it's been useful.